Okay. Let me thank you to be here, yeah, also today. Let me reconsider again. I made a mistake in uploading, but opening the presentation is not this one. I don't understand why I make always. I'm opening always the nonlinear case, which we will see in the next. Let me see. Okay, now I have it. Okay, now I see. Let me share again. I don't understand what happens here. Now, right. I hope that you can see the slide or the presentation of last time. The idea is a little bit to recap these 5 equations with a little bit the meaning, but about the meaning we will see a little bit together using an exercise. Okay, I would like to reconsider this slide here and then the conclusion. Do you remember I told you that the Kalman filter in its basic structure consists of 5 equations, and these 5 equations are split, I would like to say, into groups. We have a state prediction with 2 equations and a correction, or sometimes the second step we can find the name second approximation, again, state prediction sometimes, a priori estimation, the correction, a posteriori estimation. Anyway, in the literature, you can find different nomenclature. But anyway, 2 steps. In any case, 2 steps. This picture came from a paper, a free paper you can find in internet. I would like to invite to read nevertheless this paper, because in any case you can find some indications can help to understand. But let me look again about the meaning of the first equation, estimation state, system state. Do you remember I emphasized in accordance to the discretization of forward-Euler, this must be clear, because if you use a different discretization, we have a different estimation system state equation. This means we have a different Kalman filter. Of course, the difference could not be considered a real variation, because real variation, we will see what I intend, but anyway, it's in a different structure. I have in a project, it's not closed yet, with Rolls-Royce in Friedrichshafen here in Germany, in which for different reasons, I will tell you during the semester, we used a backward Euler approximation, or discretization, better to say. It's an approximation. Discretization is an approximation, as I told you last time, for different reasons. Or we can use Runge-Kutta, or we can use, probably you heard about, Runge-Kutta methods or OM methods. You have many methods to approximate or to discretize a continuous system. If we are using forward Euler, we have this structure here. Let me go ahead and then we will come back during the semester on these particular aspects. I don't have time to tell you much about this, but I have a course in this semester on discretization. Not related to the Kalman filter, but we can consider also Kalman filter. The name of the course is Discrete Identification Control. If you want, you can come on Tuesday. The address, the Zoom is the same, starting 10 o'clock, 15. I start with the delay, 15 past 10. Yeah, what I emphasized last time, again, hat means estimation. the true value in the sense of Kalman is without hat. But what I emphasized, you remember, we can see that on the left part we have K, let me say the actual value, if you like, and why, if you like, because you can consider also the future value. This depends what is the present for us. In the right part, we have a K minus 1. In different discretization, as I told you, it's not exactly so separated, the present with the past. This means we have to consider some problems sometimes in the causality. I don't know if you think about that. But let me go ahead with this. In particular, if the value the value u is k, this is not the problem in terms of the causality, but the problem is if x depends of k. But what I emphasized last time, more than this, is that we have a minus here, and here we don't have minus. The reason is we can explain, let's say, explain or clarify, considering the recursivity nature of the Kalman. We can see, in fact, here that you can see here, and we can clarify with this expression here, in which the output of the second step, this means the output of the Kalman filter, is used for the next step. This means I will consider the actual value or the past value, if you like, as again, at time k-1 as the output of the Kalman filter. Therefore, this element here is not minus because it is the corrected state or the state vector at the step before. Therefore, we have a difference between this x hat and this x hat here. It's not only in terms of, let me say k, because k represented the prediction, the prediction, if you like. But we have a difference because this without minus, the index minus, is the corrected. The prediction depends on the past corrected and what I am doing with the input now. Same consideration can be done here for the error or the error covariance matrix. We have an a priori error covariance matrix, and we have an a posteriori error covariance matrix. But the a posteriori is calculated or is considered at the step before, which depends at what I have in the second step. These three equations, this means this equation is extremely important because it's the result at the end, is the result. Also here, we have some interesting consideration, but in any case, this equation here, do you remember, came from boring calculation based on the statistical issues when the hypothesis of Kalman are respected. Linear system, wide Gaussian noise, and independent noise between state noise and measurement noise. With the hypothesis of the equation 2, assuming that the corrected value is exactly this expression here, basically it's a linear combination of the state prediction plus kk, which is the goal of Kalman filter, which multiply this difference here, which is the innovation. You remember this element, this element here is the innovation. You have an interesting interpretation of the equation too. I don't know if you remember, I try to express that we approximate x hat an approximation. The true value of Kalman, x without hat, the true value of Kalman, the true value of Kalman is what I know plus what I don't know. I don't know if you remember this basic concept. What I know is the model. We will see also in the nonlinear system, and nevertheless represent the knowledge about my reality. Plus what I don't know, but with the hypothesis that's what I don't know is Gaussian, wide, and so on. Of course, why I'm speaking the true of Kalman. because we use the hypothesis of Kalman. What I know plus what I don't know, but what I don't know is not generic with some hypotheses. If these hypotheses are not guarantees, it's not guaranteed, it's clearly that we have to work a little bit more. In fact, we have in this sense a different Kalman filter structure, really different Kalman filter, if the distribution is not Gaussian and so on. Keep in mind that in this course, we will consider the hypothesis which I told you. We will see that we extend the case at nonlinear case. But of course, I don't have time to tell you different, we will see different variations, but always in with this hypothesis, and we will see that the nonlinear case, I will consider just one, the most important, I would like to say, streaming in the Kalman filter, the extended Kalman filter. We have two main streaming with this hypothesis here, extended and unscented Kalman filter. Okay, if I consider this hypothesis here, and if I consider, you remember, the trace of the a posteriori covariance matrix, and which is in a positive defined function, quadratic function, I don't know if you remember, is here. Yeah, which is in a function of kk, because kk is here. We have seen exactly now. Kk works in xk hat. This means if I do this boring calculation, really boring, do you remember I showed you in the book? 3 pages, do you remember this? Last time I showed you how we can calculate this derivative. If you want, I show you again. I didn't put it in the slide because it's really extremely boring, but easy in the sense because pk, or in particular the trace, do you remember what is the trace? The sum of the diagonal elements. This means the variance of my variable, because we are in the presence of a statistical variable. I mean, ek is a statistical variable because xk is a statistical variable. Of course, also here we have the content of the statistical element because it's the correction, which depends also on this Q and R. But basically, everything started from the statistical nature of xk. I don't know if you remember. Skip this calculation because I think it's still complex. Without calculations, I mean, the concept in the sense. What is x? Yeah. It's clear the statistical nature of this because we have the deterministic part. Plus, you remember this W is the stochastic vector, which is characterized by its matrix Q. We'll see at the beginning. Yeah, we can see here, which is basically is characterized by a normal means Gaussian probability distribution P, characterized by a mean value 0, very important nevertheless, and its covariance matrix. Covariance, the reason is that we connect the variable. Because if the variables are not connected, we cannot use as an observer. Remember the observability. We will see today in an easy example with one variable. And so it will be easy to understand what I intend. Because we don't speak about the variance, covariance matrix, but just about variance. In any case, this function here is in a positive function, convex function. This means this condition here, I don't know if you remember in high school, and not only necessary, but also sufficient. Remember when we find the minimum of a function, the derivative, x square y equals x squared, no? The minimum difference, 0, no? Or x plus 1, everything up to 2, the minimum at x equal 1. So how we can calculate? You do the derivative and you put equal 0. But this is just a necessary condition. Becomes sufficient when we know that the function is convex. I don't know if you remember math. No, the convex function, what is the minimum? It's the minimum. We have to calculate first derivative, second derivative. But if convex, you don't need to do the all derivatives to classify if the minimum, the maximum, or a certain point. If you know that it's convex, is enough. Not only necessary, but it's enough. Otherwise, the derivative is just a necessary condition. Because could be maximum, could be minimum. The function which have many oscillations, let me say. This means not convex. You remember the convex function, no? Pk depends of k. The derivative equals 0 allows to calculate when means where, depends. For which k we have the minimum. If you do the calculations, I don't suggest to do the calculation because I can show you here in the book. We have a 3 or the 4 pages notebook. I would like to say 2 pages if I remember well. And you have to consider that it's nevertheless, what happens now? 1 second, because probably the connection. Okay, everything's okay. I will show you what I intend. I'm able to find quickly because in this book, for me, it is difficult to find. Probably here. Okay, I found it. Let me show you what I. Look. Yeah. I don't know if it's visible. J is the trace of P. The notation a little bit different, but we can see that x hat, excuse me, x tilde is our error. Very often in the books, tilde that recall us something, yeah, variation. Anyway, look, the condition is exactly what I told you before, because J is the trace, which depends of K. I try to repeat again. And then look, you don't have to read the book in any books. You can see calculation. Believe me, it's not so difficult, but in any case, then once we have K, excuse me, we have also the value, where is, yeah, of the function P at this K. Which can be expressed also in this form. This form is an equivalent form of K. If you put here pk, we have also what I told you in the slide. Just to understand that where these final results come from. Final results are these two. At the end, we obtained these two, these two results, equation 1 and equation 3, just calculating the minimum of the trace. Now, do you remember I told you we have the trace, which is the sum of the diagonal element in the covariance matrix P, a posteriori error covariance matrix. We have the sum of all errors, let me say, in terms of variance. But we want to minimize each let me say, error. But we can demonstrate. I think the paper is I showed you last time. Yeah, he's here. Mm, I don't remember. Ah, he's here. In this paper, which I suggested, you can find the demonstration that if the hypotheses are guarantees, this KK minimize all elements of the diagonal matrix singularly. This means not only the sum, but all elements, all errors is minimal. Because if the sum is minimal, that in general does not represent, does not mean that all elements of the sum. But in this case, we can demonstrate this. Yeah, as you know, the result. This means each error is the minimum estimation error in this sense, is the minimal one. To conclude and to start with the example, I would like to emphasize again the concept of, we can see the statistical concept. We can see that the result or the equations depends of Q, uncertainty related to the system, depends of R, uncertainty related to the measurements, and depends on the initial value of P and the initial value of X. I mean, let me start with this. It's a little bit easy to be understood. To start, I need the initial value of X because, as I told you probably last time quickly, let me redraw for you. The algorithm is a recursive algorithm. This means I will obtain results recursively. This means step by step. Right. Yes. Yeah. Let me now show what I intend. As I told you, in our case, you have a convex function, which is a function, let me say, in general, of the error. But before reaching this, I will start, for instance, from this value here. This could be considered a time k, or the k minus 1 is the same, or yeah, let me do a little bit better in this, in accordance with the notation. Let me write so, or in it, it could be more clear. Initial, init. And of course, step by step, I try to explain that we will converge to this one. In any case, because the function to be optimized is a convex function. Now, it's positive because you remember it's the sum of positive elements. But of course, we need not only this element here, but also we need an initial value of P. Now, P is not exactly a deterministic function. Why that? Because X is a stochastic one. This means, let me say, we have in the region in which we have an uncertainties for P, which this element here could be here, not exactly in a possible. I mean, we have a function P which have its variation in the sense. But nevertheless, independently of the value or initial value of P or the value of X, we will converge somehow in this region here, which nevertheless we can see in a minimum. But of course, it's the minimum of an stochastic function. This means where really this minimum, or at least the value of this minimum is unclear. Again, I mean, we have a variation inside, but we will find nevertheless this value here. Let me see if I forgot to say something. I don't think so. But starting, it doesn't matter where I start. I will reach this value here. Let me go ahead with Q and R, and then we will try to implement. Q and R is extremely important because we can see from this expression here that depending on Q and R, the Kalman filter works in a different way. I mean, for large, let me start for R because it's easier. For large value of R, large value of R means that we have uncertainties in the measurements or in the data. If R is large, KK will be small. This means we can see here that the prediction or the correction or the the correction or the a posteriori correction, better to say, does not depend much from the measurement because the measurement is not. We cannot trust the measurements because we say or we assume or we know that the measurement are affected by uncertainties. This means we don't trust the measurement and we correct it based on the a priori prediction. Same consideration can be done for Q. I mean, if Q is very small, for instance, this means I trust the model because the uncertainty on the model is reduced, let me say, or relatively small, because this Q represents the covariance of the W value. W variable is the variation, let me say variation, the variance, or covariance to be precise, of the model in the sense, or the stochastic variable which I associate to the model. This means very small value of Q. Again, I will trust more the model. And what is the effect on K? If you look here, Q works in this P minus, we can see here. This means, again, K is, let me say, the minimal one. Let me consider Q equals 0, no? In which the model is perfect, no? The deterministic is perfect. We can see that we have the minimal value of the KK because we have the minimal value of PM. Okay. I think we can repeat this using the example. Let me see if I forgot to say something. Otherwise, I will open MATLAB. We try to do the first implementation. Here I told you I think I told you many things. Okay, let me open MATLAB. Do you know MATLAB already? No. Oh, I know. Thank you to be here.
Ist der Schlüssel? Wie kannst du am Haus 12 aktivieren oder Haus 16?
So hier, auch hier.
Die nur auf der Rückseite beim Lieferanteneingang. Also am besten Haus 12 oder 16. Und dann Überschrift.
Weil das sind jeden Tag.
Ja, das sind noch 24 Stunden.
Praktisch nur dort. Okay.
Im Moment.
Just a second and I come back. Today, heute ist der 18. Ne?
17. 19.
19.
Ging bis danach.
Rainer, vielen Dank, wirklich.
Ja, viel Spaß. Viel Spaß.
Ja. What about MATLAB? Do you know a little bit MATLAB already? A little bit. Okay, this means I try to explain also a little bit MATLAB. Yeah? Okay, let me open MATLAB. Let me open MATLAB. Where is MATLAB now? Let me try to fathom MATLAB. I would like to open this. Okay. Click twice. If you click twice on the icon, should be possible to open the file, or the program, better to say, is the file, of course. If you need to work at home with our resource, we have all possible licenses. You have to send me an email. I will forward your email to the technician, and the technician will contact you to work in remote. Yeah, it is possible. Okay. Okay, this means you don't need to send me an email. Is a little bit slow, but let me share in the meantime. Oh, it's slow because I open more than one program. This is the trouble. Let me try to close some of them. Because the system is slow. Probably I click twice or 3 times. Yeah, now we have. I don't know if I'm able to close now. Some of them. The problem is I opened more than one now. Let me see. Let me close this. Yeah, excuse me. The problem is no. It seems to be that I opened 3 times. Now I'm not able to close. Okay, one is closed. Okay, now I think that I close everything. Okay, let me see if I'm able to open. Oh, I don't know what happens. Did you see MATLAB now? I think, no? Did you see MATLAB? Yes, I think so. Okay. What about MATLAB? I have to a little bit speed up this part here. Nevertheless, each time which I will open in a file of MATLAB, I try to repeat. I know that for you could be a little bit difficult because if you don't know MATLAB, we have a difficulty more. But anyway, look, the MATLAB is a program which we can open if you click twice on the icon, and this is the interface which you can see. Look, here is known, this part here is known because this version of MATLAB runs under Windows. This means here is the part where we are. Here is the part where we are. We can see that at this moment, I mean, the lecture of this semester, Lublin, because I hold a lecture also at the University of Lublin in Poland, and then the other folder, the name is estimation of a constant. Under estimation of the constant, we can see here the current folder is exactly in the subfolder of Lublin and the subfolder of a lecture and so on. We have this content here. Is the what we have in the current folder. If you look here, you can see fx function. Here we can put comments, we can do some operations. Look here, 1 plus 1. We have that the answer equals 2. And A and S answer is a variable which we can see here in the workspace. We can see here on the right part which variables are present. A and S is the variable, means or recalls answer. The content is 2. If I write 1 plus 2, I override in the same variables the new results. Of course, I can define a new variable if you want, but E capitalized, very important. Between capitalized, not capitalized, MATLAB establishing a difference. I mean, E capitalized in a variable, E not capitalized in a different variable. 3 plus 4, I have the variable E capitalized equals 7. We can see that in the workspace, we have these two variables which are active. Okay, what about this? This region here in the middle is, let me say, something more active with respect to the rest, because we can see that there are many files. It seems to be that I have at disposition many files. Here's the file of today, constant estimation. But of course, in general, is an .m. M means MATLAB. M characterize the family. MATLAB means matrices laboratory. Therefore, now we can justify why I told you at the beginning of the semester many things about the matrices, continuous matrix, discrete matrix, also today trace of a matrix. Because with MATLAB we can work very well, not only with MATLAB, many other software or the tools, but MATLAB in particular. MATLAB is we have many macros, many functions. Really very well organized to work with matrix or the matrices. Here in the M file, we can really build also complex program. Look here, for instance, PSO algorithm. I don't know if you heard about PSO, particle swarm optimization algorithm or the methods. Yeah, it's not the topic of this course. It's the topic on the course on optimization, but we can use also in Kalman filter, where we can use to tune or to calculate, to tune the matrix Q and R. Because Q and R, do you remember last time I told you, really God knows. Because it's what we don't know. You remember, the truth of MATLAB is what we know and what we don't know. And what we don't know is what we cannot be modeled. Is also, do you remember last time, is the approximation which I do doing the discretization, because discretization is a stepwise could be, yeah, could be also a different approximation, trapezoidal approximation. Probably you heard about that. You can approximate a function in a trapezoidal form. Last time I told you how we forward Euler. I think I told you also how backward Euler approximate the function with the stepwise approximation. This also is something which is difficult to quantify correctly or precisely. And this is characterized in our course by this Gaussian noise, covariance matrix, Q matrix, R matrix, depends if the uncertainties or what I don't know is in the system or in the data, in the output, let me say representation or structure of the model. I will come back on this during the semester. This means how we can calculate Q, how we calculate R. The PSO is also in the method, but it's not the topic of today. Just to show you that in M structure, I can build really complex files, a complex structure. Look, for calculate the minimum in this case, while I don't know if you know this this element in the programming, but let me go ahead slowly now. This file here, the file of today, is exactly the Kalman filter. To be precise, the Kalman filter, how I implemented the Kalman filter using Simulink and MATLAB. At this moment, we are in MATLAB. What is Simulink? Simulink is also MATLAB, but is a graphical interface which allows to simplify the representation of the model. Simulink allows to really intuitively to understand what we are doing. About Simulink, I tell you in a few minutes. Let me analyze now the Kalman, how I implemented the kernel of the Kalman filter. Because with Simulink, typically, but not limited to this, we represent the system. Here, it seems that the Kalman filter is realized in a function. I don't know if you know what the function is. The function is subroutine. The function is the program which is called for the main part of the program. This means depends of another structure, depends of Simulink. Nevertheless, before clarify the software which I have, we can see here something which recall is written here. It's an a priori estimation of the state. After the symbol here, we have just a comment. Here is the active, let me say, part of the software. It is in a comment. Let me show you some intuitively at the beginning. You can see here the definition of R and Q. Yeah, I called here RW and QX. We can see a covariance of the measure. I put here current, but it's not exactly, in this example, it's not exactly current. Let me write let me correct in the sense of measure data. Yes. Because yeah, it's a parameter. I called R because what I'm measuring, because we will see later, we will use R as a possible resistance, but could be one variable, no? One variable. It doesn't matter what. Could be also a current. It's not wrong. But let me write generically. Look, here's the equation B. You remember the a priori estimation of the covariance of the system. These three equations characterize my Kalman gain. This is exactly the a posteriori estimation of the state. I don't know if I will come back on detail now. And here is the a posteriori estimation of the covariance matrix. Before going in depth on this code, let me show you the system which I'm considering, because it's the easiest system which I can consider. The system which I consider is this. I called R, could be also, I wrote current, but isn't a variable R. Which is a constant. But I don't know its value. Or I better to say, I measure the value, but with an error. But I know a priori, I know which is a constant. This means this basically is the model. Constant zero. Assuming that at time zero, I know, let me write a little bit better. Okay, constant zero. It's a value which is not exactly, let me say, the true value. The idea is to estimate the true value starting, do you remember the scheme here? Starting from an initial value of R. Now, this model here, or that this knowledge is not exactly a model in our sets, because the model, do you remember, in our case, we need in the dynamical model, and the dynamical model, this one. This is my a priori knowledge. I know that R of t, if you want to, you can consider the current I of t, but let me write R. Isn't a constant. This is my a priori knowledge. This is initial condition. Or initial knowledge, condition, also initial value. Which I know a priori, no? I know this, but it's not exactly, let me say, the truth. To build a model from this a priori knowledge, I have to realize the dynamical structure. Do you remember, I told you always we need the differential equations, we need the derivative of the state of the variable of the system. I mean, now I consider this variable here, which is a constant, as a state in order to build the model. Now, the derivative of this is equal to the derivative of this is equal to 0, because I know a priori that this variable is a constant. It's interesting when I say the variable is a constant. It's not wrong, but in a way, it seems that the constant does not depend on t. Yes. But you remember the concept that starting from an initial value, I will over time in our case is the step, try to estimate the value of R in this case, which minimizes the variance in this case of this variable here. This means in our structure, this R here change over time because the Kalman filter, let me say, needs step in order to find this value of R. Let me see if I forgot to say something. I don't think so. Now, from here, what I can say? I can say that the matrix A is equal to 0 because I can write this equation here in this form. This is the matrix A. I don't know if you remember. It's not a matrix, it's a scalar. It's a scalar because our system consists just in one variable. This means everything collapses in one scalar. Plus 0, which should represent the matrix B multiply U. Do you remember our general dynamical system in the context of Kalman? We have a matrix A multiply the state. We have a matrix B multiply U. Now B multiply U is 0, could be U 0, could be B 0, doesn't matter what. and we have the matrix, we can see that the matrix 8, 0 cannot be R0. I mean, could be also 0, but in a particular case. In general, Kalman should say to us what is the value of R. Okay, let me now, based on this, realizing the discretization of this. Discretization of this means, you remember, R of k minus Rk minus 1 divided Ts equals 0. If I discretize this, I discretize the derivative. This means extremely easy. Rk equals Rk minus 1. This is the approximation through the discretization of my continuous system. Let me now come back to the implementation. Look, in this function here, the name of this function is constant estimation, constant est. We have an argument which is a vector. We will see where this vector comes from. Yeah. Global TS is there because in the first implementation of Kalman, I used not an embedded function, not an embedded, we will see what is the meaning of this as a technical aspect, but I used, let me say, an old, it's not old because it's still present in MATLAB, but in any case, is the interpreted function. And we need to declare the global variable, which should be read from everywhere inside the function. But I will tell you about that as in a technical aspect. Using an embedded function in Simulink, we don't need. Look here. Input at step k minus 1. You remember, in Kalman, we need uk minus 1. We will see that this ua should be 0. Or if it's not 0, b must be 0. The matrix b. Because in the model, I don't have b multiply u. Again, I measure the variable r, but r is affected by errors, and I have to estimate starting from a wrong initial value, the true value in terms of Kalman. In fact, we will see that x2 is exactly the measurement of this constant. We can understand in Simulink in a few minutes. Here is exactly the state, resistance as a state, it could be current as a state, could be any kind of variable. At the position number 3, we have exactly the old value. The old value, I don't know if you remember, is x hat k minus 1. X hat k minus 1 after the correction. A0 I already clarified. B could be equal 0, or if I put 1, it doesn't matter, 100, U must be 0. Look here, a priori estimation of the state. I don't know if you remember this. No? X hat minus equals X hat, if you like, X hat minus K at step K equals X hat at the step K minus 1 is exactly what I told you here. Came from the step before. I show you later why I can realize that this came from the step before in the context of the interpreted structure of Simulink. Here, in our case, everything is 0. Because A is 0, and I put here B0. This means R of K, R of K, better say R hat minus. I mean, here we are inside. Inside means we are in the function in Kalman filter. Therefore, I am speaking about, here it is difficult in MATLAB to write hat minus, I put just star. In some literature is star. But it's, and our nomenclature is x hat minus equals, again, x hat minus a step k at the actual state equals x hat without minus at the previous state. I show you how I can do the previous state. In my representation here, I don't have minus, I don't have hat, because we are not in the Kalman, not yet. It's just a model. Just remember this difference, just a model. And then inside Kalman becomes hat, and becomes minus in the, on the right part, on the left part to the right, depends on this part here. Inside means in the function in our case. We will see now, we will close everything when I try to explain the disabling. This expression here can be written also in this form here. I told you once in the lecture, you can find a slide about that. Look, here is the old value of the covariance matrix. What is the meaning of old? I will clarify in a few minutes, really. We measure, do you remember H capitalized in the slides? To be precise, I have to write H capitalized, but not always in books is H capitalized. It's what I'm measuring. You remember, until now we have seen 1, 0, 0, 1, 0. It depends if I have two variables, of course. I have to select which one. First variable, second variable. Here we have just one variable in our model. This means it's one. I don't know if it's clear. Remember the matrix C, the row matrix in the Lundberger observer. Matrix C becomes in Kalman H, sometimes capitalized, sometimes not capitalized. It's important, this distinction when we speak about the extended Kalman filter, capitalized, not capitalized. Look, covariance of the measured data. We will see why one, just to test. Covariance of the noise system is invariance, because one value, we don't speak about covariance. Covariance means matrices. The connection between the error of the variables. Yes, the variance of the model, which in our case depends on the discretization. This could be also written in this form. I don't know if you remember. In our case, is 8 is equal 0. This means here we have just 1. E is the way to represent an identity matrix with dimension 1. This means just a scalar 1. If you look in the lecture, you can see this expression. Identity matrix plus A multiplied S. Here's the a priori error covariance. I don't know if you remember the matrix, the equation B. These three expressions, as I told you before, represent our Kalman gain. I don't know if it's is visible. Here's the inversion of H multiply P estimation, a priori estimation, multiply H transpose. In our case, H transpose is equal A because it's just in a constant. It's exactly the same. In any case, yeah, we have to do that plus RW. This is the, I don't know, probably it's nice if I show you which equation is. It's this one. This is the inversion. You can see here, no? And then I split it because sometimes we need to do some debug. We can see here is the numerator, no? P multiply H transpose. H equal 1. And then we will conclude, this is the Kalman gauge, you don't need, this is just to, this is irrelevant. No? It's an identity. Probably I tested something and it remain here. You can also comment this. Because Kn, we have just one component. And that is the equation C. I don't know if you remember this. We called x hat equals x hat minus plus kk multiply the innovation. Here is the a posteriori, estimation of the covariance matrix. And then here is the output. We consider 3 outputs, even though you don't need this in the Kalman filter. We need just this one. But sometimes to debug. Now, to close everything, let me open Simulink, which is the main file with calls, everything which I told you now here. Let me open Simulink. This file here is related, you can see here, that we are, in your folder, I put just, let me see. This file here, SLX Simulink, and you have nevertheless an embedded, this one. This one is in a software a little bit different, which I don't use at the beginning for the didactical reasons. And I uploaded both for you, but let me open this, which is related to this file here. But you can use also the second one. It's a little bit more difficult to be understood, in my opinion. But it's the new form of MATLAB, because directly with the embedded, we can program microcontroller directly. With an interpreted, we have to translate a little bit. In my lab, we implemented everything in MATLAB with embedded function. Then we flesh out the program in the microcontroller to be applied in the let me say in the real systems or in the process and so on. Okay. Now, what is Simulink? Simulink is a graphical interface. I don't know, first of all, autosave. Let me close. We can see in a graphical interface. This is a graphical interface based on MATLAB. Why that? Because each block calls an M file. Basically, the kernel of MATLAB is represented by M file. This is just a graphical representation, which helps, because otherwise we have to program a lot. This is a signal which we can do. Sometimes is necessary to do. If we don't have already prepared this kind of signal, it's the sinusoidal signal. Of course, we have to build. Look, let me consider exactly our case. The constant with the true value, the really true value, not the. It's the true value. In this case, we speak about the true value. What is really the system? Isn't a constant. But we measure the true value plus something which I don't know exactly, because with this block here, which you can find about the block, we'll tell you a little bit next time. A few minutes, because I show you what I will tell you next time. This block, we will find this block in Simulink MATLAB is a very huge program. I will show you where we can find this block. This block is in a random, generates random numbers if you look in the help of this block, you can see there's the white, Gaussian, and so on, in accordance with the hypothesis with which we are working. We are measuring this variable. This means we are measuring something true plus something which I don't know exactly, which its variance and so on. Here inside, we have the structure of the Kalman. We can see U equals 0, but even though if U is not 0, U is 0 because we don't have signal. If you don't put signal in input, see. If you don't put signal in input, we can see here. MATLAB assume it to be 0. We measure Y. Look here at the idea. Again, we are working with interpreted data or files, which is a different with respect to embedded. We will see the embedded during the semester. The input X, this is a function. FCN is a function. If you look here inside, we have exactly the name. Exactly, constant S. Of course, when we will consider the embedded, the Simulink structure is easier because we don't have to, let me say, to consider the recursivity. We didn't represent the recursivity in this form here. But didactically, at the beginning, I would like to introduce this because we can see that we will use the element in output. This means the corrected. For the next step, we can see from here. Now I try to clarify this. In the embedded, everything is inside. Everything is inside. We don't need the structure here. But let me start with this because it's easy to understand that we have here 3 output. This I don't use for the next step. Do you remember? KK is not involved in the next step. In the next step is involved the error and the state. Here, I will put the initial value of my constant. Here, I will put the initial value of my error, of the covariance, variance in our case. Could be also in a matrix here inside. But of course, what I can estimate, what I can say about it. Of course, nobody knows exactly this. And nobody knows exactly this. And then we can see here the vector with the component which I told you. Do you remember? The second component, what I measure. The third component is the old. Because the old is, at first time, is the initial value. And after the first time, I have the new one, the old one. Because it's the old in the sense, at the beginning is the start. And then I will save here what I have as step 1, which I used for the step 2. In this sense, for the state and for the error. Everything is based on this. Starting from this value, which is somewhere here. I don't know where. And also, the initial value of this is not necessarily correspond to this. Could be basically everywhere. Because X is the stochastic value. I don't know if this could be understood. I mean, I'm not moving horizontally. No, I move everywhere on this region. I mean, how possible to say the true could be something like that. Always inside. But we are represented with this, let me say, variance. Let me show you a couple of simulations. We will conclude. The next time we will go in depth on this because we need to go in depth. then I will start with a more complex example. Look at this. Here I need to define TS. If you run at home, please don't forget, first of all, to define globally TS. We don't need to define globally the embedded. And TS must be defined here. For instance, this value here about the choice of TS, we will tell you during the semester. Look what happens. Very, very few things. And then we will close. Here in MATLAB, I show you next time, we can also represent in different form the results. Look, I will compare here in the output what I will compare the true. Second, because with an instrument to compare, I will compare its estimation, and I will compare the measurements. Look, I didn't tell you about the initial value of X, what I put. I didn't tell you the initial value of P. I will do next time. Because of course, as I told you, the estimation depends on X initial value, depends on P initial value, depends on Q and R. This is the topic of next time. Look, we are measuring yellow. The true is 100, the red, and the blue is the Kalman filter, which starting from a totally wrong value, achieve, in accordance with the variance Q, some results. Of course, the result is different if Q is different, if R is different. If you want, I can change in order to understand. For instance, if you consider, and then we will discuss in depth next week, really, because we need to understand really this example here. Look, if you put here, for instance, a small value of R, what is the meaning? The meaning is I trust more the measurements. Because R characterize the variance of the noise in the measurements. This means the yellow information is more valid than the model. I trust them. Let me fix the idea. We trust the measurements because R is the variance of the measurements. At this moment, the output equation is just the measurement. We will see during the semester that could be also more complex. Look what happens. I am waiting for that I will follow more the yellow. Look. Because we are assuming that we can trust that the yellow. Probably now we cannot realize much differences, but I can exaggerate a little bit in order to show you. Yeah, we can see that it's more noisy, the blue, because we are trusting more that. What is the true? We don't know what is the true. I will trust more. Now we can see that I fit very good the yellow. But of course, we can approximate R. Yeah, you can see now. This, yeah. The last test, and then we will go really in depth next week. What happens This is the topic also for next week, but we will go in depth on this part, really in depth. What happens if instead of a constant, this is the topic of next time, but not only this, I will repeat this last part. We will try with different configurations from Q and R. We discuss together. But now, to show you how strong is the Kalman. No, I made mistakes. 1 second, because too fast. Yeah. Let me show you this. Assuming that this constant change over time is in a sinus function. This means the model which I assume to be valid is totally wrong, because I assume this is a constant. I mean, I implement it now as a model, as a constant. You remember, R of k equal R of k minus 1. But does not reflect the model, because this is not a constant. Look what happens. What we can do in this sense. Extremely interesting, huh? Here, I changed a little bit the code because I inverted. The true value is the blue, excuse me, the yellow without noise. What I measure is, in this case, is the red. Excuse me if I change the color, but I try to. And the Kalman estimate with the blue line. It seems that even though the model is totally wrong, Kalman understands that it should follow a sinus function. I can improve, of course I can improve. Let me share for everybody. I'm finishing. If I increase the uncertainty on the measurements, indirectly, I will trust more the model. Because I don't trust the measurements, I trust the model. Let me show you what happens. Look, Kalman fit is so clever that follows nevertheless this sinus shape. The reason is, even though the model is wrong, but I included uncertainties, not zero, in the Q matrix or in the uncertainty of the model. This means it's a constant, but with a variation. Of course, if I reduce Q, I will deteriorate the approximation of the sinusoidal. If I put Q equals 0, we will see next week. Try to do it. This means says trust totally the model. We will see we have some an effect. Now where I'm totally confused. I don't know what you can see now from where we are. What is Zoom? Don't understand where we are. Probably here, no? Yeah, now I have to put here. I put Q equals 0. Let me show you now. Look, Kalman estimate almost a constant because the model wasn't a constant. We will go in depth next time because I informed Kalman that the model is correct. OQ is 0. No? This is the uncertainties. Why nevertheless is moving? It's moving because I put a P0, not 0. This means we have the dynamics. But we can see that the mean value we will tend to a constant, mean value of this. Which constant? We can read this something. We will see next week, but in any case, we can see that the mean value could be seen as a constant. Yeah, I would like to conclude here. Excuse me for the delay. We will see next time some particular aspect of this. Yeah, let me